Good afternoon, everyone. Hope you're having a fantastic weekend. As always, I've started stream and realised the music is way too loud in my earballs. And I get to play with my microphone just as I start. Actually, I wonder if that's my audio being too loud. Hey, chat, can you hear me? Can you hear the music? Is everything sane enough for us to kick off? Would love a thumbs up. You know me, I don't trust myself, don't trust my setup, don't trust my gear. It's all good. All right, thanks, Barney. Welcome. We're kicking off at a bit of a different time to what we're used to. Normally, I, being an Aussie, have been streaming of a Australian evening. I thought today, had nothing better to do apart from some, hey, Nicholas, Tesla, how's it going, Tesla? Thinking I've got nothing better to do but some work that I brought home over the weekend. I'm like, I could do that or I could stream during the day. Hey, Breadstick, how's it going? And thought that I could try streaming of an afternoon to see if I can hit the US audience in their time zone to kind of see if I've got any US love coming in from YouTube who haven't been able to tune in because I stream at stupid o'clock their time on a more regular basis than not. So if you're from the US, welcome. Good to have you here. Apologies for the fact that I haven't done a US-centric stream before. It's just that my weekend days are normally spent not streaming. So welcome. Hope you enjoy your stay. Today we're going to pick up where we left off the other evening with ROP Emporium. And if you tuned in or if you caught it on YouTube, you will know that we beat Ret to win fairly quickly. And here's me thinking, you read left to right, top to bottom. We moved on to bad characters next. Turns out bad characters are actually probably about the 5th level. And we struggled on it. We struggled on it big time. And I ended up falling down some interesting rabbit holes. If you haven't seen that, go catch it out on YouTube. It's worth, I guess, watching me bleed if you enjoy watching me suffer. But we weren't quite ready to make it there yet. I think we're going to need to learn some techniques and some tricks in the split, callme, and write4 challenges to be able to tackle bad characters. And furthermore, for each of these challenges, let's zoom in on Ret to win because I've actually beaten that one already. You'll see that there's a bit of hand-holding. There's some text here that kind of walks you through some ideas. I'm intentionally ignoring those. I haven't read any spoilers, haven't done any of these challenges before. Completely fresh, without any of the hand-holding. So I'm guessing in the bad charts, there's probably the spoiler right on the page, but I'm not that silly. I'm choosing not to read it. So don't be reading that going, why didn't you get this? It tells you how to do it, because I'm trying to avoid that as much as possible. So, I guess we should kick off with Split. As per usual, let me know if the AV is kind of shonky. Let me know. If there's anything you need my attention for in chat, just please make sure you use my name. That way my IRC client will go ding, and I'll know that there's some things to attend to. But otherwise, yeah, thanks for tuning in. We may as well just kick it off with Split. Enough of the garbage waffling on. We're doing all the 64-bit challenges as well, just to make things interesting at Mongo's request. And I have made my terminal text a bit bigger for this stream as well, so hopefully that makes things easier to see. So we're doing ROP Emporium, and we'll work on the split binary. So each of these challenges ships with a binary and flag.text. So we're just gonna, yeah, why not? We'll overwrite the old flag. What is this flag? A placeholder 32-byte flag. So I think all the flags are all the same in each of these challenge binaries. What we need to do is we need to find a way to exploit the split binary such that we could either, I mean, this is a CTF pattern, right? You want to get this flag so you can put it into the scoreboard system so you can have fame and profit as the, or maybe just fame, as the winner of a CTF. So you've got two options, obviously, when you're doing pwnable binary exploits. You can either do what's called get a shell, which is you exploit the split binary on the challenge server. We're just going to be doing all these challenges locally today. But you exploit the binary such that you get an interactive shell. So it smells kind of like SSH, but you don't need a password. And you can use that to then kick off arbitrary commands and basically just cap the flag and you win. But the premise is that if you'd shelled the binary, you can think of it if it was a real-world target. That's a pretty interesting primitive, being able to run shell commands on someone's box. Otherwise, if you kind of want to go the more simpler, or some would think maybe more surgical approach, which is simply to have your exploit run a payload inside the victim process that simply reads the flag's files, contents, and returns it to you. That's cool too. But we, where possible, prefer to get shells because, yeah, we like to think we actually are movie hackers doing cool stuff and getting shells in people's boxes. So that's the approach we'll be taking if we can. Alrighty, so we're given a binary called split. Let's see what it does when we run it. Split by ROP Emporium, 64 bits. Oh yeah, the other thing I've been doing for all these challenges is moving split to split 64. Just in case later on we do get the 32-bit version of split, we can differentiate them by file name. So split 64 is split by ROP Emporium, contriving a reason to ask for user data. Awesome. Put in some A's and we get an exit. Cool beans. So I don't know why this one's called split. Maybe the blurb would tell us more. Combine elements from the write4 challenge that have been split apart to beat this challenge. Learn how to use another tool whilst crafting a short ROP chain. Fair enough. So if we'd actually read this, we probably would have seen combine elements from write4 and known that this probably is the second level that we should have done last time instead of bad characters, but I am not that silly. Yeah, solved. Correct, Barney. Let's move on to callme, hey? Maybe. So let's write this a little Pwn Tools harness to interface with it with. At some stage we'll also be needing to pop it open in IDA, I would suspect. Throwing up the privacy screen for a second while I map this folder. Don't want to go showing my home dir on camera, on stream I should say. You can tell I'm well prepared. I gave myself an hour. I was on the way home from the markets with my fruit and veg. Gave myself a whole hour to make that walk home, get settled, and get my stuff ready. And obviously I put that time to good use because I'm clearly very ready for this. There we go. So we've got the ROP Emporium directory. And we've got the split 64 binary. So of course it's an ELF64, no surprises there. The main function, what does it do? It calls set vbuff to probably unbuffer standard error. Yep, stood out, get unbuffered. We then just puts some banner material and then we call the pwnme function and then we just puts exiting and return. So if we have a look at pwnme does a memset where it zeroes out OX20 bytes at the pointer at this stack buffer. So this memset here is zeroing out this stack buffer, which I'm going to go out on a limb and go, this is the user input. It'll be a char* user input. So we're going to put some message, contriving a reason to ask a user for data. We print a little greater than. And then we fgets OX60 bytes into the user input buffer. I don't know why this is called split. I was thinking maybe if it was split, then maybe they would be like corrupting part of our payload that sat maybe beyond the stack pointer. Not that that would be a very useful binary thing to do. But I was thinking that maybe it would be blowing some holes in our buffer that we'd have to have our ROP chain skip over if we wanted any sort of decent ROP chain. But it looks pretty straightforward to me. Kind of curious as to how this differs from the first challenge. Anyway, let's give it a go. So we got, what do I do? Pwn split 64.py. And let's kick off this exploit. So I'll set up a tube, pwn.process, split 64, and let's go straight to t.interactive. Make that bad boy executable and run it. There we go, we've basically written a very thin wrapper around the binary that does a whole not much except for dropping us into this little interactive shell doohickey with it. Let's make this a little bit more useful. Yeah, we should be fine. We had a problem last stream with the way that I was attaching GDB. I generally try to attach GDB to a organically spawned process, but you can also basically spawn it within GDB, which is good for setting earlier on breakpoints. If we brush up against what we had last time, I'll change my approach, but for now I'll do the good old-fashioned start a process organically and attach to it. So pwn GDB attached to the tube, and as I normally do, let's set up a list of commands. We just want it to be a continue to start with. Is it GDB script? Python from pwn import. Here's a trick, by the way. From pwn import star. And you can go help GDB. So this is great for when you're doing things like, you know, sharpening your CTF skills on an airplane and you're too cheap or don't know how to do DNS tunneling to get free Wi-Fi. You can actually get all the pwn tools documentation and documentation for stuff like print. Maybe not. Len. Yeah, okay, so you can get some Python built-in function help as well. But yeah, I'm kind of keen to read this GDB page to find out. Yeah, so GDB script is a new line delimited series of GDB commands to run upon attaching the debugger. So I'll make the GDB script. I can't type today. We'll go new line and we'll join using new lines GDB CMD, which right now is just going to be a little C. But if later on we wanted to kind of sneak in a breakpoint here, you know, oxfoo, we could do that quite easily and have multiple GDB commands kick off as soon as GDB attaches. Let's go to shove a whole bunch of A's down the gullet of this thing, hey? Buff plus equals A times 1024. Actually, you know what? Let's be adults about this. fgets is doing up to OX 60 bytes. I think we'll actually do OX 5F and null terminate, but either which way, I've got a mental off by one potentially, but we'll just go shove OX 60 bytes down the line, see what happens. And I'll send that as a line. Run the exploit. And sure enough, we get a ret, and at the time of the ret, at the top of the stack, is a bunch of A's. 55 A's. That's enough for a pretty decent ROP chain, I think. I mean, if we needed to, we could do some trickery to make use of other parts of our input, but I don't know if we'll see. We'll see if we need more A's than that. Oh, it is 64-bit. Yeah. 55 on 8. Yeah, that's actually, if it was 32-bit, we'd have a lot of gadgets, but 64 bits, yeah, it's maybe a bit tight. Sneaky little check sec. We can see that the binary has NX as is to be expected for a series of ROP challenges. At least ASLR is turned off for us. Alright, now for something that is, if you tuned in last time, fraught with danger. Let's go and find the offset to that save return point overwrite. Instead of a bunch of A's, we'll do pwn.cyclic, where n equals 8. And let's see what offset we get. Great. So pwn_tools has gone and done it again. Coincidentally, we end up with a quite unfortunate string being pointed to by RSP. So if you missed out last time, I've got a feeling the ROP Emporium challenges are all going to perhaps use the exact same stack layout. So what's just happened here is if we go and generate a OX 60 byte oop, phone's not on silent, my bad, where n is equal to 8, meaning that every 8 consecutive bytes, or every chunk of 8 bytes has to be unique. Nope, we don't need the pwn because I've imported as star. You'll see that this is the buffer that got thrown down the wire. And this little slice here, the kind of most unfortunate slice of them all, ended up being in the save return point overwrite slot. Which is a shame, but it's what we've got to work with. So we'll go and grab that there. So offset to the save return pointer equals pwn.cyclic find. That string for a cyclic pattern of n being 8. And then this here, this cyclic find will basically tell us how far into that cyclic string this pattern appears. So buff plus equals, let's just go back to the good old-fashioned bunch of A's. A little pattern here that we use to basically give us flexibility. Right now it's just going to print out this number of A's, but if we were to go and, you know, sneak some stuff in there, this number would automatically adjust for us based on what we've already shoved into buff. Buff plus equals B times 8. Buff plus equals C times 16. And we should get a crash. At the time of the crash, RSP should point to a bunch of B's, followed by a bunch of C's. Let's see how we go. There we go. So at the time of the ret, a bunch of B's at the top of the stack, and then a bunch of C's. So we're at a good place here to kick off a ROP chain. Now, what do we want to do? What do we want to do? What have we got? We've got a function called useful function. Maybe this is what's going on here. I think maybe in the previous binary they straight up give you useful function that would pop shell. In this one we got one that pops bin ls. Actually, this is starting to look a lot like that challenge we got stuck on last time. So we do get the binary using system, because we can see here with a very short function list, it's a dynamically compiled binary. If we wanted to use stuff in libc that wasn't dynamically compiled in, we'd have to manufacture an info leak and go walk through libc looking for the function we want, but we're given a pointer to system already. So if we want to make use of that pointer to system inside the binary, we're going to need to basically be able to put a string at a place in memory. So system takes a char star. We need to go and put a pointer in. Let me just go and quickly grab my handy dandy little 64-bit ROP cheat sheet. Here it is. Here's my 64-bit ROP cheat sheet. 64-bit takes pointers to functions in registers, not on the stack like it does in 32-bit. So we need to make sure we populate RDI with this char star, this pointer to a character buffer, containing the command we want to run. So we're going to need to put a string in memory somewhere containing sh, for example, or find a string in memory containing sh. And then basically invoke a ROP chain that kicks us into this system function. At the time of that kicking into system, we need to have the register RDI pointing at that sh in memory. So RDI can't contain sh, it needs to point to a place in memory where there is sh, where sh is the program we want to run, which of course is just a shell. So this is actually giving me flashbacks to last time. Because right now you can see that, yeah, a pointer to the string bin ls gets put into EDI before the call to system, which is weird. You'd think that that'd be RDI, but maybe the binary was compiled in a way that the pointer to this command is going to be for sure 32 bits, but what? Strange choice, compiler. Putting the offset to the command in EDI, not RDI. Oh well. We need to find some way of repeating this sort of pattern where we put the char star of the program we want to run. In this case, bin ls sounds boring. We'd rather run bash or sh. And then we need to fake a call to system. Let's see if there's any instances of sh in memory already. Oh, that's helpful. There is a string in memory that is /bin/cat flag.text. Right, so that changes everything. We could go the hard way through this one and insist upon putting a sh somewhere into memory and then returning to system with RDI pointing at it, or we could just point RDI at this cat flag.text. Return to system, and we'll at least get the flag. I mean, it's not a shell, but I'm kind of keen to just do this the easy way so we can move on to the other challenges. Maybe we can come back to it another day and actually try and shell it, if possible. This looks like a place where we could practice what we were doing last week without the bad characters getting in our way. So maybe we should come back here to kind of refine that pattern at some point, but I think for now we're just going to do the good old cat flag. There's a string baked into the binary called useful string. Fantastic. So let's go and bake this into our exploit. We've got a pointer to cat flag. So we're going to need that. We're going to need a pointer to system, or pointer to system PLT at the very least. Here's the PLT here. Here's system. So this here, once executed, will basically jump to system for us through the magic of the PLT and the GOT. So we'll go and thieve this pointer. Pointer to PLT system. We need to make sure we're not using any bad characters in here. I reckon the only bad character we've got is probably the new line. If nulls are a problem, we're in a lot of trouble. But we definitely can't have new lines. Look, there's no 0As in here, so we're fine for new lines. The last thing we need is some way of basically having a ROP chain, which will go here, that causes this pointer to be put into RDI. And then we can just write to that by making it one of our gadgets. So we're going to need basically a pop RDI. The way I'm going to go about finding that is to use opt ROPper. There's two ROP gadget finders that I like. One is called ROPper and one is called ROP gadget. Generally, if one makes me unhappy on a given day, I'll go use the other. I haven't really kind of dug into the major differences between them just yet, but they both seem to do activities like find me a pop RDI pretty quickly. And as well as that, PETA has some support as well. If we just go and crash this sucker, we can do ROP gadget. It'll give us a ret, a pop ret, and an add ESP8 gadget. As well as that, you can do a ROP search for pop RDI. There you go. I mean, we've got that one there. If we were to do that using something like ROPper, we go ROPper-F for Twitch, ROP Emporium. Is it split 64? Yep. And there you go. You've got a whole bunch of stuff here. And here is a pop RDI ret. Potentially even the exact same one that PETA just found us. So ROPper is great for ROPper and ROP gadget are fantastic. They can do some automatic ROP chain generation for basically disabling NX for you, and then you can just go and just jump straight to shellcode. But apart from that, they give you this kind of smorgasbord of ROP gadgets. You can just kind of go through and pick and choose from the list of gadgets. You might be kind of sitting there stuck for inspiration, going, "Oh, what do I do from here?" You'll just go and just punch out this list of ROP gadgets and go, "Oh, we can use this to populate a whole bunch of registers. We can do that. So it might just be good for inspiration, as well as just giving you basically a pick list of stuff when you're struggling for pointers. But we'll just go and use PETAs right here. And the thing about ROP we covered last week is ROP is basically code reuse where you stitch together the last bits of... I've just noticed we might have a bug in our exploit. I've probably given it too many characters. It truncated at 4 bytes. Yeah, I've given it too many characters. Get it n equals 9. We can fix that in a second. It did the job anyway. But code reuse is where we kind of stitch together the tail parts of various functions throughout the binary that appear just before ret. Or, I think ret is OXC3, isn't it? Go examine 2 instructions at this address. Let's go and examine 1 byte here. Oop, that's not what I wanted. B for byte. Yeah, so OXC3 is your ret. So basically what any sort of ROP gadget finder will do is it'll search through memory looking for any C3 and then walk backwards, and due to the magic that Intel being a variable instruction length architecture, it'll kind of, from any single C3, it might go, oh, from here onwards you've got NOP-RET, which is pretty useless. Or it might look here and go, you've got the instruction 66 with the operand 90, then a ret, whatever 66 might be, sort of thing. So it's yeah, that's how ROP works. It kind of abuses the fact that there's all this existing executable code throughout the program already. It looks for anything right before a ret, and then you can stitch together Frankenstein's monster approach your choice of ROP gadgets into a ROP chain. Anyway, here's our pop RDI ret. So let's go and grab that pointer. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I caught too many characters there. We've got a pointer to, what was it? Pop RDI ret, wasn't it? Yeah, it's pop RDI ret. Pop RDI ret. Alright, we can stitch this together into something that cats the flag for us now. So here's our data that comes after the save return point overwrite, or at the save return point overwrite and onwards. So the first gadget we want to do is buff plus equals pwn.p64. We want the pointer to pop RDI. And then we want the pointer to cat flag. So when this gadget gets returned to, it's going to cause this value on the stack to be popped into RDI. And then as part of the pop, RSP will increment by 4. No, decrement by 4. Increment by 4. Increment by 8. 64 bits. To kind of point the RSP at the next gadget on the chain, which is going to make our pointer to system at the PLT. So there we go. Once this ROP chain kicks off, it'll go and put a pointer to the cat flag into RDI, and then hopefully get us into system. Let's actually step through this ROP chain. That might be an interesting exercise. Really quickly, I'm just going to go and crash this sucker. No, I'm not. I'm just going to go and pull the callme return out of IDA. Grab that pointer there. Alright, so I'm going to set a breakpoint on that return that we were crashing at before, this one here, the callme return, so that we can kind of step through our ROP chain kicking off inside GDB. Looking good to me. Let's run the exploit. Alright, so the breakpoint got hit on the ret, and the stack points to, the top of the stack points to our pop RDI gadget. The next pointer on the stack is one to the cat flag.txt string, and then the third pointer is a pointer to system at PLT. When this jump gets executed, off we go into system land. Now if we go next instruction to step into this ret, you'll see we're now at the pop RDI. So when this pop RDI hits, we should see RDI instead of pointing at a bunch of A's. Ooh. Ooh. Alright, we can shell this because I didn't think to check what the registers looked like at the time of the crash, but just so happens to be that RDI points at some of our string already on the stack. We can just go and put a shit null byte right here, and we'll get a shell. Let's step through this one here while we're doing it. This pop RDI is going to put this pointer into RDI, which is a pointer to the string cat flag. And then we're going to ret, so we can see that RDI now contains a pointer to cat flag, and we're going to ret to system. So if we let this program continue, dash got executed and nothing happened up top. We did not get our flag. Interesting. Ah, there it is. We just had to make sure end of file got sent. So there you go. We stole the flag, but I reckon we can shell this. Let me show you what I just saw. Here we let's go and create two ROP chains. ROP chain for cat flag. There we go. So we'll go and stash that ROP chain to cat the flag up here. Just quickly, let's go and crash this guy again. Let's go B's times. Let's go and drop 64 B's on the stack. Right over the top of and continuing past the save return pointer. So at the time of the at the time of the return to the smash save return pointer, we can see that RDI actually points to a bunch of A's. 39 of them followed by 55 B's. So we should be able to go and drop null byte within our stack smashing payload and just ret straight to system, because system will then kick off at the time that RDI is pointing to happy days, interactive shell. This should work. So what we need to do is we need to find the offset that RDI is pointing at within our stack smashing input. So instead of 64 B's, we'll again go and do the trusty pwn.cyclic of length 64 under n equals 8. So we have every chunk of 8 characters being unique. And we'll see what RDI points at. Run that sucker. Oh, I've got a breakpoint sitting around. That's not a problem at all for this. Don't mind me. I went and put the cyclic pattern right after all the A's, and I knew it was those A's smashing it. I went and put the bloody cyclic pattern after it anyway. That's not what we wanted. Let's keep this here as buff plus equals B times 64. So instead of this is going to be a bit weird. Instead of enough A's, according to offset SRP, excuse me, minus length buff, let's go and make this a cyclic pattern of length offset SRP minus the length of buff. Pwn.cyclic of n equals 8, and this will tell us the offset at which RDI is pointing at. There we go, so RDI is pointing at 1, 2, 3, 4, 5, 6, 7, 8. That's almost the start of our string. I think it's about 8 bytes in. So let's go the offset to RDI. That's not a great name. Equals pwn.cyclic find n equals 8. Now it's not the offset to like control of RDI. It's the offset to where it's the offset within our buffer to where RDI points to at the time of the crash. Offset RDI. That'll have to do for the time being. And for the rest of the time, I'm not going to revisit that decision. Now to make things simpler, we can get rid of all this malarkey about pwn.cyclic. We can just make this a bunch of A's again. Now, we know that this bit that RDI points to appears earlier than our bunch of A's. And this is why I do tricks like this, where you do the number of A's being the offset minus the length of buff so far. We can just go and sneak in a cheeky little buff plus equals A times offset to RDI minus the length of buff. And this will just fix itself up automatically. We can just go and kind of shim in extra stuff before all these. We'll make these be B's now. We'll make those be C's. Buff plus equals null byte. Just go and drop a cheeky little in the middle. And again, this will automatically update, which means that the C's will still be at the right spot. The will be at the right spot. RDI should point to at the time of the crash, and the crash will occur because now there'll be a bunch of C's overwriting and continuing on past the save return pointer. Cross our fingers and see what happens, hey? Time of the breakpoint, we've got the ret at the time that C's, actually I should have made that 8 C's followed by a bunch of D's. Any which way, let me just quickly check. Yes, RDI is what we want. We can see the RDI point to the string sh. Happy days. I'm just going to quickly do one last sanity check. Let's make this 8 C's. Followed by a bunch of D's. Yeah, so the ret occurs while there's a bunch of C's at the top of the stack, showing we've got nice tight rip control. And RDI points at the string sh. So what we need to do now is simply swap in, instead of these C's, we don't need these D's anymore, that was just a proof of concept. Instead of these 8 C's, we just need the 8-byte pointer to system, which we can copy from right here. Here's what we prepared earlier. This should just give us a shell. So we've got a buffer here that once sent down the line, or sent as a line, I should say. There's going to be a pointer to system that overrides the say return pointer. And at the time that the vulnerable ret happens to this pointer, RDI is going to point to sh. Let's make a note of that. RDI points here. Save return pointer overwrite. Cross our fingers and hope we get a shell. Let's go and get rid of this janky breakpoint. We don't need nothing slowing down our roll while we get our shell. Got end of file, really? Why? Correct. Why not do from pwn import star so you don't have to put pwn dot everywhere? That is a good question. It's a personal preference that I have. I don't like the idea of that in case I need to pull in other modules that have function names that clash with the pwn function names. Also, to someone who reads my scripts, they know exactly what I'm utilizing out of pwn and exactly what I'm utilizing out of other libraries. So it makes it more clear as to where I get my functions from. And it also means I don't risk polluting the global namespace and having function names collide under my use of other libraries. No dramas at all. Good question. Because you're right, it probably does get annoying seeing you go pwn dot everywhere. But that's why I do it. Why did this execute dash and then the interior process exited normally? Why do we get an end of file? I definitely have a t.interactive, yeah. Why did I get into file? Bizarre. We can see that the parent process, the vulnerable process, crashed with sigsegv. That is to be expected because that parent process did kick off child process dash, and then process 2136, which is what it kicked off, exited normally, so a successful exit from the sh. And then the parent process then proceeded to walk onto stuff on the stack that it wasn't meant to, which is what caused that sigsegv. I mean, we could drop a pointer to exit inside our ROP chain that would ensure a clean exit by the parent process, but cleanly, like, who needs clean exploits and sensible things? Why did this sh exit straight away? Is it because of the way in which this binary is running? There's no stood in, has kind of... Can it not see that it's got a terminal attached to it and it's tearing itself down or something? In which case we can probably just do cat pipe sh as what we system, which should result in system having stood in kept open by cat. Bizarre. Let's try the cat pipe sure hack. I mean, is this just my tooling? What if we don't attach GDB? It probably won't make a difference. Yeah, we've got end of file. Yeah, if we make what we execute, because I mean it's a system call that we're having. It's system that is executing this char star, or sorry, it's this character buffer. So because it's system, we can use pipe because it's getting passed straight to sh. What if we go in system cat pipe sh? That should result in sh sticking around because it's got an interest in what cat has to say. Alright, let's get rid of that cat. I don't think I should be needing that. Let's go put a break on system. Why is RDI pointing at null? Let's go bring back that breakpoint on this ret. What just happened? Why did that breakpoint not fire? Oh, I put the breakpoint on the ret from main. My bad. It's supposed to be the ret from pwnme. Let's try it again. Alright, so here's the breakpoint on the ret. At the time of the ret, RDI points to sh. Why is it the time the system kicks off, RDI is getting destroyed? Alright, so we're inside system with the PLT, then a jump there occurs. RDI still points to sh. Alright, now we're inside system and RDI points to sh. What's going on? Go back to that cat pipe sh. So yeah, RDI points to cat pipe sh. Set a break on system. Continue. Now we're in system. I'm executing cat pipe sh. Continue. We're not getting into file back now, but we're not getting standard out and standard error either. Maybe once we exit, we're going to get it all. Nope. Weird. Cat pipe sure should work, yeah? Yeah, there we go. Alright, I'm going to take a quick 2-minute breather, and we'll be back in a couple of minutes to figure out why is this shell not popping. So, go grab yourself an ice cream or something. We'll be back in a minute. Oh wait, are we back? Oh, we're back. I was thinking my hotkey wasn't working, so I was getting garbage in my shell, but no, the hotkey did work. We did come back. I just didn't have OBS open, so I couldn't see we were back. Let's try that again. And we're back. Alright, so if you've been watching chat, Barney said, so yeah, Wolf, yeah, sockets with bytes and strings. That's exactly where I've had, Python 3 having everything be Unicode, which is actually the way we should be going because we do need more than 127 characters in this world. But yeah, Python 3's handling and preference for Unicode has meant that when I try and work with ASCII, or was thinking I was working with ASCII strings, things kind of went sideways. In the case of things like, you're right, sockets were probably where I was actually having problems. Barney said, is one of the other registers with junk data causing system to exit? No, Barney, it's not one of the registers with junk data. If we go and read the man page for system only takes one argument, so it's, it considers RDI and ignores the rest, but it doesn't ignore the stack pointer. The stack pointer points on the stack at the time of our ret to system below our sh. So when system then kind of grows the stack upwards for its own personal use, it is undoubtedly corrupting our sh by virtue of using the stack where our sh happens to be. So we have to either move the stack away from us. This is, 64 nops aren't going to save you here. We either need to move the stack pointer above our sh string, which is going to be very tricky in ROP land, or we need to perhaps abuse the fact that RDI points to our string at the time of the crash to copy it to a writable part of memory with a more static address, and then reference that. Now, do we get any copy primitives in the binary? We get memset. We could maybe use memset to paint stuff in memory, but nah. We do get fgets, but as we explored last time, ropping to fgets is really hard because you've got to finagle standard into the third register. We don't get a string copy or a mem copy. So copying our string might be not doable. Can we pivot the stack to... Yeah, you were somewhat close. Well done, Barney. Can we pivot the stack above our shirt string? Probably can. Maybe. Let's have a look. Let's get rid of this shirt business for now. Let's just keep in mind that our A's are going to be useless. Wherever we see a bunch of B's on the stack, at the start of that is where RDI points to. At the time of the crash, right? And we'll get rid of this. Oop, that's not what I wanted. The 8 C's are what we're going to crash on to then have a look in memory. So the beginning of all of our B's is where RDI points to at the time of the crash, and the A's are just padding garbage. Let's go and run this. Okay, so we've got a breakpoint set on the crash. Let's just go and crash away. Let's go and telly at RSI. At RSI, $RSI. There we go. Alright, so this is what the stack looks like. -1. Useless. The stack looks like this. A single lonely A, followed by 39 Bs, and here they are, printed in kind of... This is just helpful data. We can see that we've got... at the top of the stack we've got A, and then 7 Bs, and then 8 Bs, 8 Bs, 8 Bs, 8 Bs, and then a save return pointer overwrite. So RDI points to this B here. And here is our save return pointer override. So we probably perhaps maybe want to pivot the stack up 40 bytes, like pivot RSP to be minus 40 of itself, so we need to subtract OX40 from RSP. No, decimal 40, not OX40. And then we'll kind of put the ROP chain at the beginning, but then the second and third character of our ROP chain, second, third, fourth has to be shit null byte, and that's not really desirable. Now this might be tricky. We could always try and manipulate RDI with some increments to kind of try and put the sh more towards the end of all this, and then kind of pivot RSP up to here. Let's go have a look at the gadgets we've got to see what we've got in the way of pivoting. Let's turn off the colorization. Is it dash dash no color? Yep, so dash dash no color. So when you try and grep colorful text, weird things can happen. Grep for RSP. What do we get in terms of manipulating RSP? Not a lot. Yeah, we can add RSP 8 ret. Is that actually what we want? No, adding it would move it down the stack. Right, yeah. Whereas we want to be able to subtract from it to point it up above our string. That's kind of garbage. We don't really want to dig into system and kind of try and put the string in a place that system doesn't corrupt, because people with different libcs might have systems that use the stack differently, so we've got different dodging to do. Yeah, we've got a pop RSP. What is that going to do for us? Not a lot. Now we can use that to pivot RSP to somewhere, but we don't know where to pivot it to because the stack is going to move around on boxes with ASLR. This is a tricky one. Here I was getting excited that at the time of the crash we controlled what RDI pointed to, but it looks like it may not be as kind of immediately useful as I was thinking. What else do we get in the binary? Okay, let's just quickly check. Can we ROP search for pop RDI? Yeah, we know we have that. RSI. Yeah, so we can pop RSI. What was the third? RDX. Can we pop RDX? No. So we cannot trivially control the third argument. So mem set. Yeah, the third argument is the size t. We don't get good gadgets for controlling that. We don't get any gadgets for controlling that. Let's do this and grep for RDX. It was RDX, isn't it? Yeah. Yeah, that's not a great gadget. Alright, I mean, we've got the cat flag payload. We can either drill deeper on this binary or move on to the next. Shout out in chat if you got any preferences to whether we move on or kind of dig deep on this one and try and shell it. I'm trying to do everything with Python 3. Keep screwing up. Yes. Yep. Yeah, same. Forgetting damn brackets. Can you do something weird by re-entering the vulnerable function? Level, yeah, I mean, it's pretty easy to kind of kick this off into a loop, isn't it? And that is actually what we did last stream, where I basically re-entered the vulnerable function to infinite loop the kicking off of a ROP chain so that I could manufacture an arbitrary memory read. Well, the breadstick wants us to move on. Any other last words? Is anyone super keen to see this, or should we go look at some other challenges? So good idea level, that is something we definitely can do. I can't think of how it really helps us out for this one. Barney wants to try and shell it. Alright, next person to say something decides what we do. Either that or Barney and the breadstick fight to the death, and that'll decide what we do. Quiet chat today. I think I've got more Aussie fans who are probably busy on their Saturday arvo than I do US fans. Alright, I'll leave you to kind of decide for a second while I think about if there's any last ditch ideas. You might be able to do this easier on a different challenge. Point was to get the flag, you may as well be working on. Yeah, alright, good call. We can kind of keep this in the back pocket and come back to it if we need to. Let's move on, hey? Let's see if we can actually get 2 wins in an evening. That'd be nice, wouldn't it? Callme, chain calls to multiple imported methods with specific arguments to see how the difference between 64 and 30-bit calling conventions affect your ROP chain. This is starting to sound interesting. Good call on moving on. No, I don't want 32-bit. Sloppy clicking on my behalf. Shell it, correct. Let's keep going. Alright, we're going to move on. Sorry Barnes. Sorry, correct. We'll hopefully be shelling this one. We'll see how we go, hey? Callme.zip and we'll unzip it. Oop. Ooh. This looks different to what we used to. We get an encrypted flag, 2 keys, and libcallme. Interesting. What does callme do? Hope you read the instructions. Exiting. Alright, can I get a volunteer to kind of check out the instructions and tell me kind of the minimum I need to know to be able to do this in a sensible way? I'm trying to avoid spoilers. If you're telling me, if someone says like, yeah, the instructions look like you should read them, I'll go read them. But if I can get someone to go check out the instructions for callme on ROP Emporium, tell me if there's something I should be peeking at, but there's no spoilers and they're worth reading, I'd appreciate it. In the meantime, I'll just get the mechanics kind of set up for callme. Barney's 100% down for moving on now. Dynamic library. Thought shell it means move on. No, correct. To shell it means we'd be exploiting in a way that gives us a interactive shell. There's no spoiler, so I should be good reading it. Alrighty. How do you make consecutive calls to a function from your ROP chain that won't crash afterwards? If you keep using the call instructions already present in the binary, your chains will eventually fail, especially for 32-bit. Consider why this might be the case. Alright, I'm going to read this to myself. I suggest you do the same. Alrighty, yes, this does look a lot simpler now you read the instructions. So of course the PLT is used to resolve function addresses in imported libraries at runtime. So my understanding of the PLT, let's actually go look at it in IDA. So here, for example, is puts in the PLT. So puts in the PLT is executable code, returns an integer, and it takes a single char star as an argument. And the body of this function in the executable, and we can actually have a look at these segments of the binary. And you'll see the PLT is readable and executable. The executable body of this is a simple jump into a offset stored at this location in the binary. So this here is actually called the GOT. So the GOT is the global offset table. I think it's the global offset table. It contains it's basically a table of pointers into they point at functions in loaded libraries. Because when you load a library, right, if the system's got ASLR and you're importing an ASLR library, the system's going to put that ASLR or PIE library at a random spot in memory. So A, the library will move around. B, if you dynamically link to, let's say, libc, which is what the puts function is in, then you don't really know when you compile the binary what version of libc all your users have. Nor do you know if they've kind of gone and recompiled it or if they're using a standard operating system distribution of it. So within any individual person in the world on their Unix box, within their libc, all the functions will be all different sorts of orders in all sorts of different places. You're kind of not guaranteed to jump to a consistent place inside everyone's libc, and there you got puts. So the loader basically will resolve it dynamically and cache the location of puts in the GOT at this location, is my understanding. Now, by default, I think the data here is a pointer to the lookup routine, maybe? So that the very, very first time you basically call puts at PLT, and this happens, at this offset, there will be a pointer to the loader function that basically is like, I don't know where puts is, I'm going to go do some heavy lifting and find it, I think. And then that heavy lifting function will basically store its result in the GOT. So it's like, hey, next time the program needs puts, the address is at this location in its GOT. So I don't need to keep looking it up and I can go to the pub and have a beer. Whereas, yeah, the very first time you call puts in the binary, that resolution has to occur and the caching within the GOT occurs. So when we're talking here about the procedure linkage table, resolves function addresses in imported libraries at runtime. That's my understanding of the mechanics of how it works. But it is worth reading up about because I am probably wrong on the nuances of it. Even better, go ahead and step through the lazy linking process in a debugger. We might do that. We might get lazy and just kind of breeze past it because I assume I've got an understanding, but it may be worth loading this up and actually kind of stepping through that resolution of puts to see it be resolved and see it be stored in the GOT. It's important you understand what resides at the addresses reported to you by commands like rabin2-i and rabin2-r. I've actually got rabin. Let's go see what they mean by rabin-i. Rabin-i, callme 64. Maybe I don't have rabin. Rabin2. Okay, rabin2. I'm silly. Callme 64. So rabin2 is part of radar. So the imports list, let's say fgets here. The other option was rabin2-R, which lists fgets at 0060 instead of 0040. So obviously the imports table that's being reported by rabin2 on the -I, and the relocations table being reported by rabin2 upon -R, two different sets of data. Let's see if we can match this up. Like puts in the PLT, the address is 4017F0. 4017F0. So this rabin2-I lists pointers to functions in the PLT, the procedure linkage table, and maybe this here is pointers to the GOT. Let's have a look. So here is puts in the GOT 602018. Puts 602018. So there you go. You got rabin2 minus small I and minus big R for looking up the PLT and the GOT respectively. So you don't need to go and shell out the money for either to look those up. You've got that for free in Radar 2. And if you're not happy with its performance, I'm sure they'll give you a refund on your Radar 2 license. So that's what this is saying about the PLT. Correct order. To dispose of the need for any RE, we'll tell you the following, and I'm kind of glad because I didn't want to have to reverse engineer these three functions to decide that I needed to call them one after the other with the parameters 1, 2, 3. But there you go. We need to basically call me 1, call me 2, call me 3, with the arguments 1, 2, 3 each time, and apparently the flag will be given to us automatically. So the call me functions are not in the binary. You can see that they're not here. Oh, here we go. They're listed as extern. So I'm guessing if we pop a new IDA just out of interest and pull in that dynamically linked library, or that shared object file, I should say, I'm guessing the call me functions will be in that shared object, lib call me. Yeah, so here's call me 1, call me 2, call me 3, and we can see here that, yeah, it's basically comparing var 14, which is being pulled from EDI against 1, there's a comparison against 1, comparison against 2, comparison against 3, so it's basically all these three functions are doing just a small dumb check to make sure you call them with the right arguments. If not, it dumps you out with the message incorrect parameters. Otherwise, it uses the key.dat files to do some printing by the looks of it. Well, that's what call me 3 does anyway. It does some printing. Does call me 2 do any printing? No, it looks like it just does some probably decryption. Fair enough. We just need to call these via the PLT with the correct arguments in the correct order, and we should get the flag automatically. Would love to see you trying Binary Ninja at some point too, once you get the hang of it, that is. Challenge accepted. Oh, Binary Ninja. Let's see how we go for call me. Not call me. Call me? Hang on. Binary Ninja. Call me 64. Let's at least load the binary itself. Binary Ninja. Let's cross our fingers and see how we go with Binary Ninja. I'll leave IDA open in the background if we need it, but at Wolf, your wish is my. I'll think about it. And here we go. Let's try using Binary Ninja. Oh man. Alright, let's move that out of the way. That's not at all what I wanted. Move win 2, 4. Number 2 will be our exploitation window. Alright, did some shuffling. Twitch, ROP Emporium. Bim, call me. No, pwn. Call me 64.py. And we'll go write our boilerplate again. I know that's incredibly exciting stuff. T equals pwn.process. callme 64. GDB commands is a list containing the string C. Phone.gdb.attach to the tube. Is it GDB script? From pwn import star. The reason I do from pwn import star in my little documentation reading instance of Python is because you can't do things like help pwn.gdb. Just importing pwn, you've got to import them as star and do help GDB, I believe, which is a bit annoying. GDB script, I can never remember what that is. GDB script is the name of the string of GDB commands to execute upon attaching to the process equals a new line used to join a list GDB command. Interactive. That should do it. Make it executable and run it. So we get GDB popping, and we get the message, hope you read the instructions. Happy days. Let's go build this buff up. A times 1024, t.send line buff. Run it, we should get a save return pointer override. Yep. A lot of room for a big ROP chain. We crash on the pwn.me ret. With a whole bunch of it. Why have they given us useful function in this as well? Okay, just to basically ensure that the 3 functions in that shared library are being put into the PLT. That's what useful function does. We also get useful gadgets. The pop ret. So there you go. They were kind to give us a very, very useful gadget. In fact, I'm going to thieve that now, having seen it. When you see this in a binary, pop RDI, pop RSI, pop RDX ret. If we recall, RDI, RSI, RDX are the 3 magic x64 registers used to parameterize function calls on 64-bit. When you see that, that's gold. We'll just go and steal that straight off the bat. I'm using IDA again. I'll close it so I don't accidentally do that. Force of habit. Sorry, Apple. Alright, so if I was to have read pwn.me and looked at it in this view and scrolled down a bit, I would have gone, oh yeah, useful function. Oh yeah, useful gadgets, and Binary Ninja hasn't actually disassembled that in a way that would have made me go, aha, that is a gadget that I want in my life. Binary Ninja did not disassemble this function for us. It left it as binary data, probably because this function is not being called. Is the useful function being called? No, there's no cross references to it. I think the cross refs probably come up down here. Yeah, you can tell I know my Binary Ninja. But yeah, useful gadgets didn't get... So have I been saying decompiled? Disassembled. The useful gadgets function didn't get disassembled. But obviously it's got a symbol because it knows to name it, but it didn't actually go, oh, this is code, I should disassemble it. I guess we'd simply create a function at the symbol. There we go. If we create a function at the symbol, it's gone and known to disassemble it for us. Right-click copy address. That's kind of cool. I don't think IDA actually has that, does it? I'm not going to open it and try it now, because otherwise I'm going to accidentally start using it. Go away. Alright, so this is this here is a pointer to pop RDI, pop RSI, pop RDX. Copy address. Let's go and thieve it as promised. Pointer to pop. I used to call this one pop args when I come across it. Was it pop RDI, pop RSI, pop RDX? RDI, RSI, RDX. Alright, So we've got the pop, pop, pop ret action going on for our pop args. We need to find the offset to this save return pointer. Buff plus equals tone.cyclic 1024, where n is equal to 8. Shove that down its gullet and see what crash we get. We get a crash on F followed by a bunch of A's. Yeah, so the ret happens, that's at the top of the stack. Foreground. Offset to the save return point equals OX that. No, it doesn't. Pwn.cyclic find that pointer inside a cyclic generated pattern of n equals 8. No, that's not a pointer, that's a string. There we go, that's better. So we're going to do buff plus equals a bunch of A's. That's better. Offset SRP minus the length of buff. Go and jam 1024 B's in there. So we should get a crash with the top of the stack being 8 A's. No, 8 B's. Followed by a bunch of C's. And here's our pointer to pop args, which will come in very handy shortly. Alright, so at the time of the ret, a bunch of B's on the stack followed by a bunch of C's. Awesome. So we need to execute callme 1, callme 2, callme 3 in that order with the arguments 1, 2, 3 each time. Easy done. No, you didn't, Barney. I wasn't really too keen to go reverse engineering that shared library anyway. I need to use that somewhere. My housemates bugged me to do something. Is that the your wish is my I'll think about it? You're welcome. You can keep that. What's cheating? I don't know. Was that me using IDA accidentally? Wolf? Is that what's cheating? Okay, so let's go get pointers to the PLT for our functions. So callme 1. This doesn't make it too clear that we're in the PLT, unfortunately. But we can see that this int64t callme 1 does a jump to the callme 1 at the GOT. So yeah, that looks like the PLT. So we'll need to copy that address there. Point it to PLT callme. Is it callme underscore 1? Yeah. Callme 2. Nope. Copy the address. Let's go grab the address of callme 3. Here it is. Copy that. Alright, so we've got pointers to the PLT for all our 3 callmes. And we've got a pointer to pop args. We know that we need to put 1 into RDI, 2 into RSI, 3 into RDX, which thankfully is the order, or conveniently is the order that the pop args gadget runs in. So here's where our chain starts. Buff plus equals pwn.p64. We want to go drop our pop args gadget pointer. Buff plus equals pwn.p64. 1, 2, 3. I think it's 1, 2, 3, isn't it? Yeah, 1, 2, 3. So 1 is going to go into RDI. 2 into RSI. 3 into RDX. And then a ret, which will take us to this here, which will be buff plus equals pwn.p64. Pointer to callme 1. Now, after a function returns, is it going to have restored its arguments in RDI, RSI, RDX? Probably not. fact, let's go and join this up into one line. So this here is a gadget address, followed by 3 kind of arguments to that gadget, which are consumed by these 3 pops. So this single line here is something we can just kind of copy paste, because that's what we do when we want to build an exploit really quickly. That still remains quite clear as to what it's doing. Yeah, clearish. Let's just go copy paste. So after this, we return into the first callme1. We want to then return into our pop args 1, 2, 3, repopulate those 3 registers, and then we'll go to callme2. Whoops. Repopulate the registers, and then go to callme3. And we should be done. We'll just drop into t.interactive and hope that we get a flag, I guess. So just to recap, we've got a whole bunch of junk on the stack here, just to get us out to the offset, or to get us to the save return pointer. Overwrite the save return pointer with our ROP chain. Well, at the point where the save return pointer is on the stack, from there onwards we just go... Sorry if that was a bit loud in people's ears. Didn't mean to pop into the microphone. We just go... That's better, raspberry. And we just go and drop our ROP chain onto the stack, starting at the save return pointer. So we start by populating 1, 2, and 3 into our 3 registers using this pop args, very, very handy pop args gadget. Return to callme1, restore the registers, callme2, restore the registers, callme3, cross our fingers and hope that during the interactive we get a flag, maybe? See how we go. There we go, 1 flag. And then the process stopped with exit code 0. That was nice. I'm guessing that maybe the shared library at the end of callme3 doesn't exit? Yeah, it calls exit. That's what meant that we actually exited cleanly out of our victim process, rather than just going off into crash land after we got our flag. It's like, got my flag, don't care if it crashes now. Easy done. We got our flag. Any questions, concerns, queries about the 2 challenges so far, where we basically just reused a function that was no, we didn't reuse a function. We abused a string that was already in memory and then returned a system to get a cat flag going on. And the second one was doing just what the doctor ordered, which is to execute these 3 imported functions, one after the other with the 3 correct arguments, to just magically get the flag. Any questions? There was the line on, I'll think about it. It was using IDA. My bad. Sorry, Atwolf. I'll try and see if we can stick with Binger for the rest of this stream. I mean, admittedly, Binger looks super, super slick. Like, it's a nice looking tool. I just need to kind of get used to it. And I mean, as we all know, like, IDA is differently featured, but it's pretty well known that it does have more toys and more options and more power. I mean, not necessarily stuff that I use or can afford to use. You know, if you can shell out for the decompiler license, or the decompiler plugin, it's like hacking on easy mode. You just press F5 and it's like, boom, here is some C-like code rather than trying to read assembly. And I mean, if you look at the architecture list as well for IDA, it's mind-blowing what it supports. Not that I use it for pulling apart binaries, apart from x86 and x86-64. But like, it is just supports Game Boy ROMs, for example. IDA Pro supports, a lot of embedded stuff. You know, you got your MIPS, you got your ARM, you got all sorts of crazy embedded controllers, PowerPC. Like, I'm pretty, like, I know Binary Engine does support some of these, but we know that IDA is more powerful. Not that I use it for what it can do, but I did buy IDA kind of back in the day before Binger was around. If Binger had come out before then, would I have considered it? Definitely. And I've got Binary Ninja now, thanks to Sec Talks Melbourne, for putting it up for a CTF prize. And I'm going to keep paying my maintenance on IDA because I'm hoping, like, fingers crossed, one day I get into the kind of work where or the kind of CTFing where the advanced features are needed. But yeah, I mean, if you're in the market for a disassembler, Binary Ninja does look quite nice, and the pricing is also very attractive. So we'll stick with it today and see what we can get out of it in terms of mileage. Yeah, had I not looked at the challenge, it would have been like the second one the other night. Yeah, exactly. So IDA debugger is awesome. It's really all that Binger is missing. Interesting. X Storm US X Storm. I hope you don't mind if I call you Storm. I haven't actually used the IDA debugger. I've kind of tended to use debuggers as debuggers and disassemblers as disassemblers. I probably should learn how to use the IDA debugger so I can kind of get a graphical view of the process executing. But it's just not something I've looked into yet. Alrighty, thanks everyone. I'm going to take another quick 5-minute break. When we get back, let's have a look at getting into another challenge. Hey, go grab yourself a second ice cream. Alrighty, we are back. I suppose I'm not quite ready to pack it in for the day yet. So we're moving on to the next challenge, I suppose. Write4. Find and manipulate gadgets to construct an arbitrary write primitive and use it to learn where and how to get your data into process memory. This sounds good. This sounds like they're going to give us the material we need to do the sorts of things we've been wanting to do so far. And then next up is bad chars, so hopefully after Write4, maybe we'll know the trick that they want us to use and that they've made possible within bad chars. Fingers crossed, hey? So, Write4. Did I just download the... No, I did the 64-bit one, I think. Learn or delegate, that's the way at Wolf. Not to me, though. I'm too busy to go build new binaries, but I'd love to. Maybe we'll have a chat sometime. So Write4 will unzip it. And what do we get? Flag? Yeah, sure, you can override it. We get a binary and a flag. So if we run Write464, give me the string already, there we go, we exit. So let's open up Write4. In Binger. Small looking binary. And we'll start writing our... You know what, I'm sick of writing that harness. Let's go get the pwn callme and copy it to pwn write 4 64.py, and we'll gut the stuff we don't need. Don't need these pointers, don't need the offset. All we want is a bunch of A's. Alrighty, so let's run this pwntools file. Need to learn to Python. Write4 does not exist. That's because it's called Write464, isn't it? There we go. Alright, so we get a segfault upon a ret with the stack full of A's. Not altogether too surprising. I need to find the offset, so instead of a bunch of A's, we do pwn.cyclic 1024 with n being equal to 8. Top of the stack, we've got F and then a bunch of A's again. Offset to the save return pointer equals pwn.cyclic find of that string where n is equal to 8. And buff is going to be A times offset SRP minus the length of buffer so far, followed by B times 8, followed by a bunch of C's. Really, I didn't need to gut that old exploit so hard. A lot of it is turning out to still be relevant. Run this guy, and we should get a crash at the ret. B's at the top of the stack, followed by a bunch of C's. So we're in good shape. Let's go have a look in Binger. pwnme does the good old memset, zeroes out OX20 bytes at var8, which we can rename to be user input. How do you rename? You do use n like in IDA. So straight away I don't really... I kind of like the way that IDA shows you all the locals and all the arguments at the top of the graph view for a function. But well, we only got one local in this function anyway. So we zero out the user input buffer. We get puts a message, go ahead and give me the string. We get interesting way to show me a string. Can't mouse over it. You can see in this pop-up here that what we're pointing at is 3e20 null byte, which is a greater than symbol space string of 2 bytes greater than space. We're printfing that, and then we're doing RDX is going to be stood in. Rax then goes to RDI later on, so RDI is going to be the user input, and we're getting OX 200 bytes from the user using fgets from stood in into user input, and then we're doing a nop and then a leave and then a ret. I don't really like that IDA hides the actual assembly for the leave, but well, fair enough. What has useful function got for us? Useful function ensures that there is a system pointer in the GOT, and there's system entry in the PLT. Yeah, so we get fgets, we get set vbuff, that's kind of useless. We get an fgets, memset, printf, system inputs. We don't get a gets, unfortunately. Looks like we're in the territory where we were before, except now we know that it wants us. The name write4 indicates we need to learn how to write stuff into memory and create ourselves an arbitrary write primitive using what is a pretty small binary. How are we going to do this? What are we going to do? I mean, fgets is not really giving us too much love, because you need to put the file star in the third argument. What do we get in terms of ROP gadgets? Twitch, ROP Emporium, opt, ROPper, ROPper.py for the file, write4, 64, no color, grep RDI, so we get a pop RDI, RSI, we get a pop RSI, pop RDX. RDX is the third one. Yeah, there we go. RDX is the third argument. We don't get a pop RDX. So this is where they want us to actually trot out a technique that we've been trying to and failing to use so far. So I've got a feeling we're going to get a little bit stuck here today. I'm guessing the spoilers on the write4 page would tell me what I need to know. Let's see if we can make do without those spoilers. So we can get a pop RDI, pop RSI. We don't get a way to control RDX with a gadget. What's in RDX at the time of the crash? Tell you what, is that RDX? That wouldn't be stood in the file star for stood in, would it? Spoilers on the page. Yeah, thanks, Barney. Go back to pwn me. So RDX probably actually already contains the stood in pointer at the time of the crash. Gee, I hope that at the time of the crash the other night, RDX didn't contain the stood in pointer that the time that I'd spent hours on something the other night, because that would have gotten us home and hosed really quickly. Let's assume at the time of the crash, actually, you know what? Let's set a breakpoint on this here. Let's copy the address of this move stood into RDX, and then we'll continue through the crash and we'll see if they match. Can you move another register into RDX? Men's, no you can't, because my grep for RDX across all the gadgets gives me one gadget to do with RDX, and it is hot garbage. Great for rip control, but we've already got rip control, so not that interesting. I'm going to set a breakpoint at the time at which RDX gets populated with stood in, and see if at the time of the crash RDX is still stood in-ish. And then, I mean, maybe depending on an arbitrary libc implementation of fgets, it may destroy RDX, so this might not be a completely portable exploit, unfortunately, if someone's fgets damages RDX. First step first, Hi dude, how's it going? Welcome to chat. Welcome to the channel. Good to have you here. Yeah, men's, there's not a lot to do with RDX, hey? So we've got that breakpoint there. Let's see what happens. Segfault. This is what we were having the other night. The binary is already at the read by the time GDB attaches. So we'll comment that out. Instead of doing pwn GDB attach, we'll do pwn GDB debug. I think debug just takes an argument, which is a string, which is the binary that we want to launch inside GDB. And it also takes our friendly old GDB script. So we're not having write4 64 start up organically as a normal process, and GDB will be starting it for us. And hopefully that means it doesn't cause any weirdness to occur. Let's try this again. GDB server's not installed. We had this problem the other night. Sudo apt update. So running stuff inside GDB from the get-go under pwn tools requires GDB server, obviously. Search for GDB server. It's probably just called GDB server. There we go. Sudo apt install that. And run our exploit again. T is not defined. I know what we've done. Pwn GDB debug will actually return our tube, to which we can then do our send lines in our interactives. Just had to catch what GDB debug was pooping out at us. Alright, so here's a breakpoint. I'm moving the keyword pointer at rip plus this into RDX. So I'm not actually moving this into RDX or that address into RDX. I'm moving what is at that address into RDX, which is, I think it's a file star, which is it a handle or a file descriptor for stood in? If we go next instruction, we'll see that RDX updates to become this pointer. I'm just going to grab that real quick and stash it here. So we've now got stood in at glibc in RDX. The file star is in RDX. So now if we continue through to the crash, time of the crash, RDX contains this. Is it the same? No, it is not. So at the time of the crash, we actually don't happen to already have stood in RDX. I don't think, even though this points to a null byte. And 0 is the file descriptor number for standard input. Maybe the file star... Here's a crazy idea. Man, F gets file star stream. If we just make that be a pointer to null, is that standard input? How does how do file stars work? Just gonna do some random Googling, see if we can find Unix file pointer stood in. See if there's any discussion around this. The man page for stood in. Does anyone know if we just make the file star when it comes to the third argument of f gets be a pointer to null? Is that good enough to get input from standard input? I mean, we can just try it, I guess. We can just try launching ourselves straight into an fgets ROP chain that assumes that, you know, at the time of this crash here, RDX points to null already. Will that be sufficient for us to get standard input fgetsing going on? I'm going to put that on my list of things to try and read up about. You know, it does kind of indicate in this man page here. Each of these symbols is a std.io macro of type pointed to file. Files are a buffering wrapper around Unix file descriptors. So FD012 is standard in, standard out, standard error. The same underlying files may also be accessed using the raw Unix file interface, that is, functions like read and lseek. Blah blah. Note the mixing use of files and raw file descriptors can produce unexpected results and should generally be avoided. Hacking stuff is all about making flat rocks do unexpected things, so not altogether surprised we might need to wade through this swamp at some stage of our lives. But the masochistic among you, POSIX section 823 describes in detail how this interaction is supposed to work. Maybe if there's any masochists in the channel, they could check out POSIX.1 section 823 for us to see if we can actually just get away with either having RDX be null or RDX point to a null. I wonder if this is just going to work for us. Alright, Hydra, looks like you're in good hands with Men's here, answering some questions for you. fgets has dummy byte stood in as 0. Leak is not implement. We can implement a leak. We can actually basically infinite loop the vulnerable function and keep on printfing, or we'll just keep on putsing with a ROP chain to implement an arbitrary memory leak. We'd have to basically manufacture a leak if we really needed one. But I wonder if we just leave RDX being this value, which is a pointer to null, will that let us fgets? Let's just give it a go and cross our fingers, hey? I need to get some pointers out of Binger. So I pointed to the PLT's fgets. That. There's no new lines in there, that's happy days. We need a char star. fgets takes a char star, yeah. It's a char star, so we need a char star, so just some writable part of memory. How do we look at our segments in binary ninja? This is where I start to come unstuck with my bingering. Segments, here we go. So we've got a read write there. So here's our read write. So inside BSS, let's go to BSS. This is where I normally stash stuff. So we can write anywhere past 601.088. So let's go like 601.090. And that's a good place to go. 601.090. 601.09. Let's go OA0 to go and well and truly put it beyond the end of BSS. So pointer to writable, I'm going to call this a writable area, is that 601.0A0. In fact, if we go and crash the binary and have a look here, we should just see nothing at all. Yeah, a whole bunch of nulls, so that's a place we can write to. We just go and check the VM map in GDB quickly. 601.080. 601.080. We've got plenty of writable space there till the end of the page. That should be enough to just go and ret to fgets. So instead of our B's and our C's, we'll do buff plus equals pwn.p64, pointer to plt fgets. Now we need some gadgets to go and populate RDI and RSI. RDI being the first parameter to fgets, RSI being the second. That's fine. ROP search, pop, RDI. RDI is the first one, yeah, yep. So this here is pop RDI ret. Pointer pop RDI equals OX, no, it's that, which is this here. And need to point it to pop RSI. And GDB just crashed because I have taken away its pwn tools that had actually kicked it off. ROP search for pop RSI. Copy that. Clean all this up here. Alright, so fgets, let's just go and quickly drop the signature of the function here. There we go. So into RDI, we'll go buff plus equals, so we'll do a gadget pointer, pwn.p64, pointer to pop RDI. P64. This is going to be the char star, which is going to be the pointer to writable. So into RDI goes the pointer to writable. And then we need the size in RSI. Buff plus equals pwn.p64. Let's go on my string equals hello world. Let's go and drop hello world into memory if we can. So the int size is going to be the length of my string. And that needs to go into buff plus equals pwn.p64, pointer to pop RSI. So pop RDI is going to put the pointer to writable in RDI. Pop RSI is going to do the pop RSI and put a p64 of the length of my string into RSI. Then we've got this pop R15, we've got some garbage here. Buff plus equals pwn.p64, OX, nope. Yep, OX, dead beef. Dead beef. That's just junk that goes into R15. This here goes to, this is the int size. It goes into RSI. And this here is the char star S. It goes into RDI. And then we've got our pointer to fget. So if we let this ROP chain execute, it'll achieve the painting of our two registers. We'll put some junk into R15, and we'll just use the fact that a pointer to a null is already in RDX, and cross our fingers that that causes a read from standard input to the writable part of memory. So we want to send line buff, and then we want to go t.send my string, and we should be able to send the string hello world, and then the fgets of lend my string should simply eat that and put it into memory. If this all works, we'll get hello world in memory, which will be huge, huge, I tell you. Do we have any breakpoints? Yeah, we've got a breakpoint on that file, the scripter being put in memory. Let's just go and put a breakpoint at the end of the pwn.me function. So we can step through our ROP chain bit by bit. So we'll save that, run it, and just cross our fingers and hope we get a string into memory. So we've got a breakpoint being hit, the ret happens, and we do our pop RDI, putting our writable pointer into memory. So here's our pop RDI ret. And then we do our pop RSI, where we go and put the length of my string into RSI, which is OXD. And then we've got this useless pop R15, where we just go and put dead beef into R15, which we don't care about. And here we've got a ret to fgets, and at the time of the fgets, RDI is a pointer to the writable place in memory. We'll copy that pointer right now. RSI is the length of the string we're putting into memory, and RDX, hopefully being a pointer to null, with 0 being standard inputs file descriptor number, might just work. I don't know much about file stars, which you may have seen me reading about here, but hopefully this just works, and I need to actually learn how file descriptors versus file star actually works. Yeah, that's something I need to look into. So how about we just let the binary kind of continue now until the crash, and then we'll just check. So if we just go and grab this address here now, and we examine one string at that address, we'll see it's empty string, just a bunch of nulls. If we continue till the crash, I wonder if we'll get hello world put at that address. So we get a crash here. If we examine one string there, empty string, nice. So that did not work. We actually got a crash inside of fgets. R9 plus OX8. Yeah, okay. It's trying to offset from that null byte, probably the null byte that RDX was pointing to that at the time that fgets kicked off. So no, you can't just use a pointer to a null byte as your file star when you want some fgetsing to occur from standard input. That's apparently not how it works. So I'm going to take a quick 2-minute breather, and when we get back, we're going to have a look and see if we can work out how to get an arbitrary write primitive out of this binary. So stick around, grab yourself a third ice cream, and we'll be back shortly. All right, we are back. Welcome, Foffy. Good to have you here. By the way, everyone, I'm terrible at kind of reading handles. I'm going to call kind of people things like Foffy and Barney and Men's, and if anyone kind of has a preferred way that they like people to address them, please let me know. I'll do my best to kind of keep it in mind. But Foffy Scrimshaw, you're a front-end web dev, and you like Python, but this is over your head. Welcome to the channel. Really good to have you here. So yeah, what we're doing is we're using Python basically to write an attack tool. So mostly what we're doing when we look at stuff like Binary Ninja here, and when we look at stuff like GDB here, we're actually debugging a compiled C binary. And in the case of Binary Ninja, we're disassembling a C binary. So the Python that I'm writing is in some ways kind of the less interesting part of this stream. What we're really aiming to do is understand how this C binary works, understand the way in which it's vulnerable to exploitation. It's got a software vulnerability in it, and we're really just writing, honestly, I write pretty sloppy Python. We're writing some pretty sloppy Python to basically talk to the API that this C binary has, which is simply to read things from the standard input stream. You know, if we were to go and just run the binary, which is write4 64, you'll see here when you run it, you just get to like type stuff and press enter. That's its API. So we're writing Python to interface with its API over standard input to feed it naughty strings that take control of the program. So in terms of the Python we're writing, we're really just kind of building up a really long, nasty, evil string that takes control of the C program. So that's kind of what we're really looking to do today. It's not so much kind of learn Python, but use Python to write an attack tool that takes over a C binary. Yeah, Barney, get to work, eh? Do the website stuff. We believe in you. So yeah, welcome, Foffy. Really good to have you here. So while I was away, I took a quick look at just what was on my screen, and I noticed, I'm not sure if the other day, the binary from the other day was like this. In fact, it wasn't like this. The binary from the other day had some garbage after the fgets in the pwnme function, and that was there to call bad characters and destroy our input. And so I didn't kind of give it too much thought. But really, this here, from there through to here, Binary Ninja doesn't let you select ranges. From this line, 7EC, through to the ret, 806, that's actually one big whopping ROP gadget that we might have some interest in. What it does is it populates RDX with the magic stood in. It then loads the effective address of RBP minus OX20 into racks, which then later goes into RDI, and it loads up ESI with OX200. Calls fgets, doesn't nop, does the leave, and the ret. If we can find a ROP gadget to let us control RBP and repoint that 0x20 bytes ahead of our writable section in the BSS, this here is just one big gadget that actually does us some good, that actually reads OX200 bytes to our writable area. So the question is, can we get RBX control and load an arbitrary value? Sorry, RBP control and load an arbitrary... the second time I had it right, I confused myself there. RBP. Can we get RBP control and load an arbitrary value into RBP? Furthermore, since RBP is actually a special register, it is the stack base pointer, Does that cause us any trouble while our chain gets slid through? I don't think it does. Maybe it does. I think we can probably work with that if and when RBP gets used. We can make sure that having it hang out in the BSS region isn't doing us harm. So I think this here is actually a cracker gadget. I'm going to copy that address here and make a note of it. Pointer to the gadget fgets equals that. And what does it do? It sets up RDI, ESI, RDX. Call fgets. Nop, leave, ret. And what is it doing? So RDI is going to be RBP minus OX20. RSI is going to be OX200. And EDX is going to thankfully be stood in. So then going to call fgets, execute a nop, leave, and ret. The leave. If we've got a busted RBP at the time of this leave, we're probably going to corrupt RSP, aren't we? What does a leave actually look like? Yeah, it is the breadstick. Vim is amazing. Don't you overwrite that with A's? The breadstick, I'm not sure what you're saying about overwriting with A's. What does leave actually look like? I want to crash. I don't think I want any of this anymore. It's kind of garbage stuff there. Buff plus equals BB, let's go B times 8. Gets crash. Thank you, Petter. Thank you for collapsing leave into its own single instruction. X86 leave. What does it do? Set the stack pointer to base pointer, then pop the base pointer. So what we're going to do is when we hit that leave, we're going to go and pivot the stack to be about OX20 down our ROP, our writable section, which is fine. We'll just have to make sure we go and put the rest of our ROP chain over in BSS. And because it's down the stack from the start of our thing, which is where we would have put the shirt, we're going to have a shirt at a place we know, and we're just going to have a ROP chain hanging out just below it. This should be fine. This should work. Let's see. So what are we doing? Buff plus equals pwn.p64, pointed the gadget fgets, and that gadget fgets is going to set up RDI to be RBP minus OX20. So we need to set up RBP as well. Set up RSI to be OX200, set up EDX to be stood in, call the fgets, not leave ret. That leave ret is going to pivot our chain to be something inside what we write to the writable pointer. We need to get RBP control first. So where's my ROPper RBP? So here we've got a pop RBP ret. Yep, pop RBP ret. So we've got a nice tight, no new lines control over RBP. pointer to pop RBP equals that. And what does it look like? Pop RBP ret. So we want to buff, we want to append pwn.p64 pointer to the pop RBP, and into RBP we want to put buff plus equal pwn.p64. We want to put this writable pointer. So we'll make note that at the time of this, RBP equals pointed to the gadget echoes. We actually don't want to make it the pointer to the gadget echoes. We want to make it that plus 20 to account for this minus OX20 going on over here. All right, and this chain here is going to do fgets to this as a char star, our pointer, of size OX200 from stood in. Happy days. So we want to send that line. We don't want to do this my string bizzo anymore. So after this t.send line buff, we'll go so that sending of the buff is going to cause an fgets to happen over in BSS, and then BSS will then be used, part of BSS will be used as a ROP chain. So we want to call this, we'll call it buff2, kind of like the second stage buffer. Buff2 is empty string, buff2 plus equals shirt, and then a null byte, because that's what we really want to put into memory, because this binary gives us system. Yeah, binary gives us system inside PLT. So we need a shirt somewhere in memory that we know. And then we want to buff plus equals A, just junk, times OX200 minus the length of buff2 so far. Let's go lift that OX200. So the totlen of buff2, in fact we'll do buff2 totlen, has to be OX200, because that's what this fgets is actually getting. Buff2 totlen minus length of buff. So we then need to t.send line. Send should do. We have been doing send line of our fgets buffs so far, so I'll do a send line of buff2. So what should happen? This ROP chain here should cause the fgetsing of buff2 to this place in memory, and then we'll end up with sh at this location, 6010A0, followed by a null byte, followed by a bunch of A's, and I reckon we're going to then get a crash because the stack should get pivoted into the middle of our buff2, about OX20 bytes away from the sh. Probably exactly OX20 bytes away from the sh. Let's just cross our fingers and see what happens. Do I have any breakpoints? I've got a breakpoint. That breakpoint for... is that there? This here. Yeah, so that's the pwn me ret. I'll leave that breakpoint on. See what happens. Breakpoint gets hit. So at the time of the ret, we've got a pointer to pop RBP, and then we've got a pointer that will get popped into RBP, which is 6010A0. Is that right? 6010A0 getting popped into RBP? I don't think so. I added OX20 to the wrong thing. Good thing I checked. We don't want to offset the pointer to the gadget fgets by OX20. we needed to offset our pointer to writable by OX20 because we want the RBP to be that. That was just poor form. Let's try that again. I knew it didn't look right. Alright. Yeah, C0, that looks better. So we're popping 6010C0 into RBP. And then we're dropping ourselves back into the middle of pwnme during the moving of standard input into RDX, and then we kind of continue on to do the F-gets. And then I think that's going to cause the stack to be pivoted. And if we continue here, we should get a crash on a ret where the top of the stack is A's, and we've got our magic sh in memory. Fingers crossed, let's see how we go. Crash with a whole bunch of A's at a ret, and see, look, this stack, this is actually in BSS. So we've actually gone and basically changed the program's idea of where the stack is to be inside BSS. Whole bunch of A's. We can basically just redo the same exercise now where we calculate offsets and set up more of a ROP chain. The thing is, if we examine one string at OX6010A0, we've now got sh at a static location in memory. This puts us in a really good spot. We just system that and off we go. Although now we're at the exact same problem we were some time ago, because system sh appears on the stack above the top of the current stack. And we risk having system overwrite that string anyway. Delightful. We can probably use that pop RBP followed by a leave ret to go and pivot the stack again to somewhere not near sh. Yeah, so we've just gone and found out that by controlling RBP and then doing a leave ret, we can pivot the stack to a defined location in memory, which drags the stack away from our sh. I think we're going to need to do that, otherwise we run the risk of a system overwriting our sh during its execution. Or we could do the good old nop sled trick, just by putting a bunch of ROP nops on the stack, and hoping that the system doesn't reach so far up as to ruining our sh. But I don't like that. That's not a nice approach. Where should we pivot the stack to? RBP is currently a bunch of A's, so we can probably find out which of these A's went into RBP and go straight to a leave ret. We wouldn't just need to pivot the stack. We would need to pivot this. We'd basically need to redo this operation again to do a write the stack somewhere else. So we've got a ROP chain somewhere and pivot to it, such that our sh was safe. I think I know how we're going to do this. So our pointer to writable, we'll keep it as 6010A0. But this first one here, see how we're adding 20. Let's go add 20 and then add plus OX 100, which is going to paint our sh down the stack. Then we'll redo this to paint a ROP chain up the stack, pivot to it, and know that we've got a sh down the stack. Yeah. Let's tidy this up. Pointer to sh. Pointer to our sh equals pointer to writable plus OX100 down the stack. OX100 is not going to be enough, because the right of 200 up the stack is going to destroy it. 400. If we add 400 to this, we're still not near the end of the page, so we should be fine. So pointed our shirt is going to be at the pointed writable plus 400. So instead of pivoting and writing to pointer writable, we'll write to and pivot to 2. Pointer our shirt. That ain't what we're F-getsing as the first. That's not the char star. Pointer to our sh of OX200 from studying, yeah. And then for buff 2, yeah, for buff 2 we're going to go and put a sh and a bunch of A's. But instead of a bunch of A's, what we actually need to do here is calculate an offset so that we can kind of get into this ROP chain and then continue ROPing. I'm going to delete this cruft from here. We don't want a bunch of A's, we want buff 2. We don't want shit either. Trust me on this. Buff 2 plus equals pwn.cyclic. I'm probably doing this the hard way. What I'll do is I'll solve it the hard way, then we'll go and read the page that Barney's told me there's spoilers at, and we'll find out the way you should have done it. And maybe we'll give that a go, then call it a day. I'm pretty sure like triple ROP chain is not the way they wanted me to do this, but we'll see. We'll see what their doco says. Pwn.cyclic of OX200 where n equals 8. And we'll see where in this second ROP chain we end up. So yeah, we're popping into RBP, pointed our sh plus 20, and then we're F-getsing to point at our sh of OX200 from stood in, and then that stood in is going to be this here. It's going to be OX200 bytes of cyclic, send line, and we should get a crash that lets us continue ROPing. Here it is, very familiar looking cyclic pattern at the top. In fact, we don't need to redo this exercise. We've got that offset up here. Offset to save return pointer. Easy. Buff 2 plus equals A times offset to SRP minus the length of buff 2 so far. That's going to be buff 2. Buff 2, now we'll go and sneak our null byte back in. Buff 2 plus equals B times 32. Alright, so now we should get sh painted in memory and a crash at B times 32. And sh will be at this address plus OX400. Let's give that a go. Crash on the B's, yep, 32 B's, that looks right. Let's go and examine one string at that plus OX400. Sh. So we got sh down BSS. We've got rip control, we've got a new ROP chain opportunity within BSS. Now we want to repeat what we just did to pivot the stack up and write 200 more bytes so that we can then write our I'm going to damage BSS while I let BSS be the stack. I'm going to go buy myself another 400 bytes. I think we've still got budget for 400 more bytes, so that I don't risk damaging all this stuff here and this stuff here while system executes. That's got to how you say nopsled. Yeah, it does. Don't do nopsled. Yeah, no, I didn't do it. I hope you're all proud of me. But it wouldn't be a nop sled, it'd be a ROP nop sled. Which, by the way, a ROP nop sled, a ROP nop is just a pointer to a ret. So it's like you slide through going like ret to ret to ret to ret, ret to a ret to a ret to a ret, and you just kind of slide through doing a whole bunch of NOP equivalence in ROP terms. Yeah, I was going to go buy myself 400 more bytes. So pointer to writable is going to be that plus OX400. And then pointer to our sh is going to be that plus OX400 again. So let's go and just go and thieve this here. This small ROP chain, that allowed us to paint and pivot a new stack, pivot our stack to somewhere we've just populated. Let's go thieve that. And this time, instead of painting and pivoting to point at our sh, we want to do it to pointer writable, and just go and put a general purpose stack further up BSS so that our sh down BSS, which is OX400 bytes away, which won't get overwritten by this OX200, that sh will remain intact while system executes. I think this, once I get this to work, this might be it for the night. We'll quickly go and read the spoilers for this challenge so we know where we went wrong with life on this one. And then I might peel off. I'm getting a bit hungry. Time to cook some dinners, I think. So this here, buff 2, is going to, paint and pivot to pointer writable, which is going to be our general purpose stack for the use of the system. No, when this second ROP chain calls fgets is going to destroy the sh. Dang it. Fgets is going to destroy the sh. I made this way more complicated than it has to be. Way more complicated. We don't need... Let me just back out a while. Let me back out for a bit. Here. So I've undone... Pointed our sh. No, I want to undo. I want to back out even more. Let's wind back about 15 minutes. Here. Yeah, okay. Sorry, we've rewound a bit. We're back to our pretty naive approach. Because we know where this stack is, all we need to do is put the sh down stack. It's better than the kind of using the systems stack, because the systems stack was subject to ASLR. We could have kind of put a sh down the stack and had our ROP chain above the sh. The problem was we would then need to disable system ASLR to know where the stack is, and then like cross our fingers and be like, people's environments are going to totally misalign the stack, and different distros might have different stack bases for default and all this kind of garbage. Now, because we know that our stack where we're pivoting to, we're only doing a single pivot. The single pivot is resulting in buff 2 being the new stack in BSS, and because we know where BSS is, because we wrote to it, we can have our sh be down stack, have a ROP chain for system above it, and have the system char star be the sh down stack. Yeah, this is going to work just fine. We way overcomplicated it. So in our second ROP chain, we're going to go buff 2 plus equals a times offset to the save return pointer overwrite minus the length of buff 2 so far. Buff plus equals B times 8. I'm just going to quickly do a sanity check. Buff plus equals C times 64. Let's kick that one off. Continue, and we get a crash on our Bs. Bs, then a new line? I know what I did. I forgot to do buff 2 plus equals. That's going to happen a lot with buff versus buff 2. I'm going to forget to be... this is a horrible way of string building, by the way, and it leads to mistakes like that one right there. Try again. Continue, we can get rid of that breakpoint. Yeah, so this second crash, we've got a ROP chain going on the stack. We know addresses, we know the layout of this stack, we know its base. We can just go and put our shit down stack and ROP to system, and away we go. We don't need this garbage anymore. We don't need this breakpoint anymore. So what is our new chain going to look like? System only takes one argument, a char star in in RDI, so we've got a pointer to pop RDI. Buff 2 plus equals pwn.p64. This of course is our second ROP chain. We're going to do a pop RDI, buff 2 plus equals pwn.p64. Pointer to my sh. Now I don't think sh is... Yeah, we don't have pointer my shit yet. We'll calculate that in a second. Buff 2 plus equals. I need to go get myself a system in the PLT. Grab that from there. Pointer to PLT. System equals that. Go and grab the signature for system. Simply takes a char star. P64, pointed to the PLT system. Now we need to figure out, and then we need to go buff 2 plus equals shirt null byte. Let's just go and drop the shirt right after. No, that's not a good place to put it. Oh no, that's a fine place to put it. System won't go and destroy its own. System won't destroy its parent's save return pointer. Just for sanity, buff 2 plus equals pwn.p64. Go and put a null byte there. Let's just go and return to null and cause a crash after system finishes. Really, what we probably actually should do is go and get exit. There's no pointer to exit in this binary, so we can't exit. Let's just go and crash on null. Am I missing anything in chat, by the way? Everyone's either quiet and just not using my name, or what's going on? Yeah, okay, sorry, yeah. Y'all are a bit quiet today. Sleepy Saturday Arvo, having a nap, are we? So yeah, we'll crash on here. And here is our magic string. Our golden sh. So this here will end up doing system of sh. This here will cause sh, the address of sh, I think that's what we do, to go into RDI. Then we've got a system sh, crash, golden sh. So we just need to calculate where in memory this sh is. Two options: either we just go and let this sucker crash, and go and find in memory, or we can go and calculate it. So, whoops, that's fine. Pointer to my sh is going to be pointer to writable, because remember these A's are going to be at pointer to writable. Yeah, they will. plus the offset to the save return pointer. We'll count for these, and then we've got 1, 2, 3, 4. 4 times 8 bytes for each pointer we've gone and dropped onto our second stack. So the pointer to sh is the pointer to writable plus the offset SRP plus 32 to account for 1, 2, 3, 4. This should work. What I'm going to do is I'm going to go and put a breakpoint on, you know what, let's go and put this breakpoint here back and run this top to bottom. Let's see what we get. Here's the breakpoint. Here's where we control RBP with OX20 bytes down from where we want to write to, and here's where we return to partway through pony, which results in a fgets happening, writing a new stack to BSS, and then we end up actually pivoting to it. So let's go step through these. I think NI is going to step over all these. So here's where our fgets happens, writing this many bytes from stood-in to that address. So we go next instruction. Yep. So now we should be able to examine one string at here. And yeah, we've got a bunch of A's and then some stuff. Let's go, can we tally there? So we've written to the stack a bunch of A's. Then we've got the pointer to our pop RDI. Popping the string sh into RDI. What are we about to do? We're about to do a NOP. Let's just continue on with this. We've got a NOP, we've got a leave, then we've got a ret, and we're retting to, so the stack has pivoted, and we're about to ret to the gadget, which is pop RDI, popping sh into RDI. Very nice. Pop RDI ret, and now we are in system with RDI being appointed to sh. If we just continue, we should get a shell. Segfault. Nice. We got a crash, not a shell. What just happened? I've got an idea for when you want to read the ROP Emporium page. You're enjoying the pain, is what you mean. Yeah, I'm keen to see what ROP Emporium has to say as a way to solve this. So what just happened? Let me just step back through this again. So system got sad halfway through. Why might that be? What does the crash look like? Moving racks to what's at RSP. So we've got a stack overflow, I think. D40. Yeah, I think we've just blown ourselves off the top of BSS. So we need to give ourselves some more space, I think. Pointed writable. Plus OX800. Just go and give us a bunch more space before we go and blow ourselves off the top of BSS. Looks like system wants a lot of stack space. Is that actually the shell that wants all that stack space? Because if so, we might be in a dangerous place in memory. Is there a bigger writable area in this binary we can use? Let's cross our fingers that OX 800 bytes gives us enough room. Continue. Put another ret here. So we executed a shell. And then got end of file. Gonna just what was that? Why is that red? Oh yeah, it makes sense why that red's getting hit twice. So we pop the pointer to sh into RDI. We ret to system, and system looks like it started a process, but didn't really give us much love. I'm just gonna go and stop debugging. T equals let's see if we run this out of GDB, what happens? There we go. We've got a shell. GDB was just getting in our way. When it saw system get hit and pop a new shell, it kind of detached from stuff and left Pwn tools in a bit of a weird place. So we've got an interactive shell out of the write4 binary in what I'm guessing is probably not the way we were meant to do it. So what we did was we this is our first ROP chain where we put a pointer within BSS into RBP and then kind of returned it to halfway through using. Oh, by the way, I did set up something for this event. There we go. We then returned to halfway through fgets. Hope you like that, by the way. I thought it was quite cute. And used that to fgets, basically a brand new ROP chain into OX 200 bytes into BSS. And things weren't happy until we kind of gave ourselves plenty of headroom, so we didn't blow ourselves off the top of BSS, causing a stack overflow. Fun fact, that was actually a stack overflow, as opposed to a stack buffer overflow. Two terms that get conflated quite a bit. What we experienced was a stack overflow, where the stack grew up and up and up and up until it kind of crossed a page boundary into a non-writable page. Bona fide stack overflow. So we wrote a new ROP chain into the BSS area, BSS region. And we fed in a second buffer in response to this fgets being ROPed to. And this second buffer was basically putting sh down stack in an address that we can calculate, because we know where this version of the stack is in memory as opposed to the system stack. The ROP chain loaded up RDI with the calculatable pointer to sh, and then returned to system so that we could system that sh. And then we just induce a crash in the event that the binary was to continue on. And here's our golden sh string. So one more time. Oh, I didn't do the streamers again. There we go. We've got a shell. So that's probably not really the way we're meant to do it. Let's go and read. Let's go and read the real write-up to see what should have been done. It's a little loud. Thanks, Barney. Sorry if the Windows 3.1 confetti blew anyone's earballs out. Really good to have you here, Devious Serious. We're about to kind of wrap this up for the day. What we were doing was exploitation of a compiled C binary, which is made available at the ropemporium.com website. So write4 was a C program that we could actually exploit by feeding it really weird strings to its input. So this stream will be up on YouTube in the coming hours once the upload is done. Yes, I did hit the start record button. Good on me. This video will be up on YouTube, so if you missed the earlier part, if you're kind of keen, kind of curious to see what we were doing, yeah, the breadstick got it. We ropped no, it wasn't a. Okay, I thought the breadstick was giving a sarcastic answer. That's what we did. ROP a format string exploit into the printf to write to memory using %n, then put the sh into system. Would that work? Maybe. So let's quickly have a look. Good idea. Man printf. What's the actual man page for the C printf? Man 3? There we go. Is printf in the binary? Yes, it is. So the trick with printf though is it takes a variable number of arguments. We could have potentially made this work. It may have been painful. So printf takes a variable number of arguments, and on 64-bit, the first 6 int or pointer arguments are passed in register. So we probably could have like had RDI point to a format string. The problem being the same as with system. I mean, if we were able to control RDI to point to a string we can control, so that we could use printf to then, use %x's to exhaust these, and then have on the stack be enough material to exploit a %n or to leverage printf to do a %n style format string write. If we can control RDI because printf takes char star, we could have just used system. So the thing that would have happened there, Bread, is that if we could have printf'd a string we control, we could have also systemed a string we control. Really good idea. It would have been probably wouldn't have been easier in 32-bit with stack-based ROP anyway. The trick here was basically putting into memory a string at an address that we could tell. But definitely a good idea. Let's go have a read of the way that we should have done this. Yeah, so this is along the lines of what challenge we face. We want to use ROP to get an arbitrary write primitive. Reading from memory is something we did last stream, where we actually constructed and manufactured a info leak. And famously, I think it was Helvar Flake, famously yet I think it was Helvar, who said info leaks aren't discovered. Info leaks aren't necessarily a bug class in and of themselves that you can just stumble upon. They're manufactured. So oftentimes you can use a memory corruption bug to actually create yourself a info leak primitive and an info leak mechanism. So that's what we did last stream. If you're kind of curious to see how we already knew how to create an arbitrary read primitive, granted we did that under the bad characters restriction, but we were able to create a arbitrary memory read primitive. My brain's just broken. But we didn't have a memory write primitive up until late in this stream today, when we realized we should reuse basically half of the pwnme function. Let's keep on reading and find out where we went wrong and overcomplicated this. Yep, fair. We could have used printf to read or write. Again, the problem was simply that finding that char star. We did this where we considered how much space was in the writable section way too late. I basically was getting those stack overflows. I was like, fuck it, let's give it 800 or OX400 or OX800 more bytes to work with. And whether corrupting the information store at these locations, we did consider that. I was trying my best to avoid clobbering stuff that was already in BSS, although I think more than a few times I did that accidentally. Once you figure out how to write your string into memory and where to write it, go ahead and call system with its location as your only arg. Are you going to cat flag or drop a shell? Try to wrap some of your functionality in helper functions. Pah! Who needs it? If you can write a 4 or 8 byte. See this here, this 4 or 8 bytes, and the name of the challenge, write4, makes me think that maybe we were meant to use printf as our write primitive. How would that have worked? Interesting. Can you craft a function that takes a string in a memory location and returns a ROP chain that will write that string to your chosen location? That's a pretty cool tech. I'm sure we should probably learn to do that. We kind of did that with our memory leak primitive, where we actually wrote a function that didn't simply return a ROP chain that did the arbitrary read. The function actually executed that ROP chain and induced a loop that would keep control in our hands. And then we tried to pass that function off into dinelf, but ended up with headaches. So I'm reading this here and I'm not thinking we were too far off, although this writing a 4 or 8 byte value to a location in memory makes me think that they wanted us to use format string printf as a write mechanism. But again, how would, if we could have done that? Bear with me real quick. Let me just get a crash out of this sucker. Let's bring back GDB. And let's go and buff plus equals b times 8. Let's just go and buff plus equals c times 1024. So let's go and create a crash, a very primitive crash, very early on in our first ROP chain. So RDX, hang on, what's RDI? So at the time of the crash, we already actually have RDI control, but I think we played with this early on, didn't we? Yeah, we did play with this early on, and RDI points to some of our earlier A's. And the problem was we were basically putting sh there, and then ropping to system, and system was destroying that. We suspect strongly that system was destroying that sh during its invocation. We probably should have checked that. We did have the technology. We probably should have verified that system was what was destroying that sh, or that the sh was at least getting destroyed. Maybe if you were to kind of put a format string earlier up on the stack, that maybe my libc's printf accessed that string earlier than system accessed the char star, such that it was actually consuming it before corrupting it, or maybe printf doesn't actually reach far up enough to cause the corruption. Maybe printf. There's one way to find out. Let's just quickly go and instead of this B and then a bunch of C's, we'll leave the C's there to induce a crash. Let's go and just do a really hacky slipping in of printf between the A's and the C's and see if we were able to printf some A's. If we were, that certainly would have been a viable technique. At least with my libc, that would have been viable. I mean, a lot of my exploit probably already depends, not necessarily depends on my libc, but depends on someone's libc not being too crazy different. So let's copy the address of this printf. Buff plus equals pwn.p64, address of printf. And let's at least see if we get some A's printf'd. And if we do, let's try some %x's after that. Yeah, let's do that. That looks good to me. Let's run it. So we get a crash inside printf, reading from RSP plus OX50, or sorry, moving to RSP plus OX50. At that time, yeah, printf ain't too happy. Let's go set a breakpoint to printf, on printf. No, we've already got one on the ret. Okay, so RDI, which is our first argument, points into a bunch of A's. Actually, let's go and null terminate that string. That might be what we're doing wrong. No, let's go and put 256 C's buff plus equals pwn.p64. Let's go put a null pointer on the stack. Let's try that. Segfault. Same sort of crash. F00540. There's a null byte as part of this pointer anyway, so this string of A's is null terminated thanks to this pointer. Yeah, control of RDI. We don't have control of RDI, but we have control of what RDI points to. But Libred, I mean, it looks to me as though printf is not too happy being returned to. Is there any ideas that you want me to try before we wrap this up? Lane, good to have you here. How many programming languages and tools do I need to understand this? We're in pretty advanced territory here. Welcome, really good to have you here, Lane. We're in pretty annoyingly advanced territory in kind of the ROP land right now. To know and understand what would have gone on today in terms of programming languages, you would have needed a little bit of C, a little bit of assembly, x86 64 assembly. You would have needed an understanding of process architecture and the way by which processes execute on Linux. You would have needed to know just a little bit about Linux in general and some Python to see the exploit being built. But that understanding of the kind of life cycle of a Linux process, function call and return mechanics, you would have needed quite a bit of. So it's more so not around the lines of languages that you would have needed to know, but around how programs, the life cycle of a program, should I say, on modern computers. So yeah, Libred, I'm not too sure. It doesn't seem straight away as though printf was too happy being run. So let me just go and just clean this up real quick. We don't need that printf pointer, or the C's, or that null. We don't need GDB anymore. Does this exploit still work? I should have backed it up before I went hacking on it. Yep, there we go. Alrighty, any quick last queries, questions, concerns before I head off and make myself a dinner? It's been a almost 3.5 hour stream tonight. That includes a lot of pre-roll though. Hope you enjoyed that little pre-roll clip, by the way. Some of my favorite tunes of late. Hopefully we're keeping people entertained. And if you missed it, then make sure you turn up about 10 minutes before the next stream. I'll have some beats going on. What's up, mens? What's for dinner? What am I having for dinner tonight? Probably need to go to the shops and pick some stuff up. But what do I have? I've got a bunch of veggies. I've got some beans. I might do like a Mexican style fried veggies with lettuce and rice. What time should you pop around? You're not still around, are you? You've left Victoria, right? But I mean, if you're here, you're welcome, like, right now. Is that... No, it's not you at the door. Yeah, you're welcome anytime, mens. You know you're welcome anytime. Thank you very much, Splat. Really glad you enjoyed it. Men's is back in Brizzy, sucked in. Thank you so much, everyone, for sticking around and keeping me company this afternoon. I hope you enjoyed it. We'll be continuing on. Oh, thanks, Mans. You're the best. We'll probably be having to head back to Bad Characters next time we pick up this series, which if you missed the last stream, it's up on YouTube. This one will be up on YouTube shortly. Yeah, Bad Chars was a bit of a nightmare. So we're going to have to head back into that territory next time. Thank you everyone for sticking around. Hope you enjoyed it, and I will catch you next time.